Welcome to this sixth doubt clearing session of the course Engineering Thermodynamics. So the first question for today is, sir, please explain PV graphs of liquids that contracts and expands. Okay. So what we have done basically, while I have shown you the PV graphs, I have basically taken these as nothing but projections of the PVT surface. Okay. So while we are taking the projection of PVT surface, we found that the liquids which contracts on freezing, for that type of liquids, we are having something like this, our saturated liquid vapor dome. And then at this particular point, what will be happening? Now we will be having actually some zone up to which we will be having liquid. So this is the zone up to which we are having liquid, and beyond this we will be having nothing but the combination of solid plus liquid. Okay. Now this solid plus liquid combination is such that after this particular line we will be having once again pure solid. Okay. So and then here we will be having actually somewhere over here our sublimation line. So this is this particular PV diagram is for substances which contracts on freezing. So this is for all which contracts on freezing. So what will be happening over here? You can clearly see, for example, if you are at this particular point, so at this particular point you will be having certain specific volume over here. So certain value of V, say V1. Okay. Or I can write it as a VL. Now when you will be actually finding that the substance is changing the phase, so first it will be going to solid liquid zone and then it will be going to pure solid. Okay, upon further removal of the heat, and finally we will be finding that the specific volume corresponding to this new location is nothing but Vs. Okay, so it means the specific volume at boundary, which is a separation in between solid and liquid, that is nothing but our liquid, specific volume corresponding to liquid, and the boundary at which we are having separation from solid to solid plus liquid, there we are having nothing but solid phase, so that is having less specific volume. So this particular boundary which is in between the solid to solid plus liquid mixture, that is having low specific volume in comparison to the specific volume of the liquid at the corresponding same pressure condition. Okay, so it means that this is particularly a substance which is actually contracting on freezing. If I talk of a substance which expands on freezing, so what will be happening for that particular substance? Once again, let me draw the PV axis, and this is my liquid vapor dome, and then over here we have this dotted step. So all this step I am showing dotted, and then I am showing sublimation line. Then I have one line over here which is firm, which shows the separation from solid plus liquid region to liquid, and then over here I am representing a dotted line. So the meaning of this dotted line is that we are having this line on some different plane. Okay, so this firm line whatever I am drawing, these are the directly visible line which we can see, and this dashed line whatever I am drawing, it is actually showing nothing but a line which is corresponding to a face or edge that is not actually visible. Okay, so though it appears to you over here that while you are changing from liquid phase to solid phase, once again the specific volume is decreasing, but this line is actually a dashed line, so we are not exactly knowing the location in 3D space of this line. Okay, so that's why what I will be doing now, I will show the three-dimensional plot, and in this particular three-dimensional plot you can see this is our pressure axis, this is our volume axis, and this is our temperature axis. Okay, so one line which I have represented, that is actually corresponding to this particular line, whatever actually I am moving the cursor. So you can see movement of my cursor. So my cursor is actually moving along a line. So this particular line is nothing but corresponding to the transition towards solid side, and then we'll be having some a line from the back face. Okay, so from this top view you can clearly see we are having one edge, one point over here on this towards rightward side, and one point towards the left side. Okay, so the point towards the left side is corresponding to liquid phase. So that's why if you take the projection, liquid will be having some specific volume, and the line point which you are taking corresponding to the solid side, that is actually shifting to the right. Okay, so that's why it will be having more specific volume. However, on the when we are plotting it on the 2D plane, then it is not actually giving very clear picture. Okay, so am I clear with this response? So whatever I have communicated, I have tried to communicate once again. Are you okay with that one? Whoever asked the question?
Yes, so I got it. Thank you.
Yes,
So
sir.
basically, you have to see the three-dimensional representation for actually looking into the increase of specific volume. Okay.
Okay, sir.
Then next question is, please explain the graph of PV water where you explained the concept of saturated liquid. Okay. So what I told that what will be happening, this is my pressure, this is my volume, this is my liquid vapor dome. So I told that we have started from this particular point and we have started decreasing the pressure. Because of that, we are having slight increase in specific volume, particularly corresponding to the situation where we have saturated liquid state. Okay. Now at this point, when we will be further decreasing the pressure, okay, if I further decrease the pressure, in that case, what will be happening? We will be finding a situation that temperature we are trying to maintain same, T1. Okay, so corresponding to T1, I have some saturation pressure over here, Psat. Okay, so it means if my saturation pressure corresponding to T1, if my actual pressure goes below the saturation pressure, in that case, what will be happening? Within the fluid, inherently some phenomenon will be happening which will try to make the pressure equal to that of saturation pressure. Okay. That's why when we are further removing the weight, though upon further removal of the weight, we are actually trying to reduce the pressure, but for having thermodynamic stable state, the pressure within that has to be saturated. So because of that, what will be happening? There will be evaporation of some liquid into vapor. So once some liquid is actually getting evaporated into vapor, because of that, the molecular distances will be increasing, which will be increasing actually the pressure within the system. Okay, so once molecular momentum will shift, so that will try to increase the pressure. And in order to do so, because some of the liquid is getting converted into vapor, so there will be some loss of temperature. So in order to maintain the temperature at constant value, we have to provide certain amount of heat. So because of that, what we are doing, though we are removing the weight, the removal of weight is actually relaxing the situation of pressure below saturation pressure. Because of that, evaporation is happening, and while evaporation is happening, some amount of energy is actually required for liquid to evaporate into vapor, so that energy is provided with the help of heat. So by doing so, we will be actually able to achieve the desired situation of constant pressure and temperature, and we will be having the phase transition also. So now is this point clear?
So here we the volume, this specific volume is increased because even though we kept the temperature constant, since we are constantly decreasing the pressure, that's why the specific volume is increased.
Yes, we were actually trying to decrease the, means we were removing these extra weights, but corresponding to this condition, pressure is maintained because of the formation of more vapor. However, externally we are trying to decrease the pressure.
So why is the change in specific volume so slight? Like how we determine that the change of specific volume is so small? Is it like, is it experimental value that the change in specific volume is less?
Yes, in case of liquid state, what happens basically, because liquid is an incompressible substance, okay? So for example, if you are taking 15 liters liquid in a container, so if you are now changing the pressure and temperature also, so instead of 15, either it will go to 15.2 or 15.3. There will not be drastic change in properties of the liquid, okay? Particularly the specific volume of the liquid. Other properties of liquid may change, but specific volume will be changing very less because of the incompressible nature of liquid. Okay.
Okay, sir.
Okay. The next question is, please explain the PVT surface again. Okay. So just now also I have explained. So are you clear, or still do I need to repeat it?
Sir, please explain again.
Okay. So what we are doing basically over the PVT surface, we are trying to plot the combination of all the measurable quantities. So pressure, volume, and temperature are the quantities which we can measure. So we can achieve this particular surface by different combinations. One of the combination can be we are maintaining constant pressure. Okay. Another combination can be we are maintaining constant volume. Another combination can be we are maintaining constant temperature. Okay. So if you see, this is my temperature axis. So whatever these lines are coming, these curved lines, these all lines are nothing but my constant temperature lines. And any line which will be parallel to this temperature axis and cutting at any arbitrary location on the volume axis, that will be actually my constant volume line. And any line which is parallel to volume axis but crossing pressure axis at any point, that will be my constant pressure line. Okay. Now we know already that we will be having some two-phase region. So clearly you can see that this is my saturated liquid part. This is my critical point, and then I have over here as a saturated vapor line. So anything on the right hand side of the saturated vapor, I am calling it as complete vapor phase. Anything on the left side towards the left of this saturated liquid line, that is nothing but our pure liquid. And above the critical point, as I have already told you, that we will be having instant transition from liquid to vapor. So because of that, anything beyond critical point, we are calling a common region as gas. Okay. And many a times this is also referred to as dense fluid, because our critical point will be having very, very high pressure. And if it is in the vapor phase, it will be completely compressible. So because of the high compressibility, its density will be very high. So we call it as dense fluid. Okay. Then what we have this surface over here. So this particular surface over here is nothing but specifying the solid phase. Okay. And the solid phase surface is actually more extended towards the right side in comparison to the surface of the liquid phase. So this you can see. This liquid phase curve is actually following this particular profile. If I extend it till my volume axis, and solid surface is actually starting at some point which is on the right side towards the volume axis. Okay. So it means that while we will be having the transition from liquid to the solid, so in this case, we will be having actually increase of specific volume. Once we are having increase of volume or increase of specific volume, in that case, what will be happening? These particular substances will be coming under the category where we are having actually expansion upon freezing. Okay. So this curve is clear, or do you have any confusion over this one?
Yes, sir, it is clear.
Sir,
Okay. Yes.
so what does the dotted line represent on the solid portion?
So this dotted line is actually trying to show that there is a hidden phase. Okay. So there is a hidden phase behind, and that hidden phase is nothing but actually the region of solid plus liquid, where we will be having, like we have in between the liquid and vapor transition, some liquid vapor two-phase zone. Similarly, from solid to liquid, this step transformation, we are having some common phase. So that common phase is nothing but actually the two-phase region of solid and liquid. Is it okay?
Yes, sir.
Now, if I go to, now if I move to my PVT surface for fluids which contracts on freezing. So there you can clearly see that your liquid phase is actually, liquid phase is towards the right and solid phase is on the extreme left. And this phase, whatever I was trying to show you earlier, that phase which represents the two-phase solid liquid zone is actually clearly visible over here. Okay. And moreover, while liquid will be converting into the solid, we will be having actually decrease of specific volume. Okay. So this particular substance will be actually contracting upon freezing. Is this point clear?
Yes, sir. So, sir, can we tell what factors decide that the substance will contract or expand on freezing?
What factor?
Will determine that the substance will contract or expand upon freezing?
Yes, yes, yes. Let me give you one example. So though I'll be taking up this particular portion, just wait for it. Yeah. So though I'll be taking up this particular portion in my next lecture, okay, particularly with reference to water, but let me briefly give you an idea over here only. So what we are having while we are having water molecules, so we are having oxygen bond in between the oxygen and hydrogen atoms. Okay. So in case of liquids, molecules are far apart and means molecules are close enough, but still they are not having any, they are not so close enough and their locations are not fixed. So there is no formation of additional hydrogen bond. Okay. However, when we will be shifting to the ice structure, in case of ice, what we will be having between the molecules, particularly between the hydrogen atoms, we will be actually having the formation of hydrogen bonds. Okay. So what will be happening? We will be having formation of hydrogen bonds. Once we have the formation of multiple hydrogen bonds, so what will be happening? These hydrogen bonds will actually will occupy some extra space and these will create some extra void so that the other molecules cannot penetrate through these internal structures. Okay. So because of that, what will be happening? Whatever the number of molecules we were having in certain amount of mass of liquid, now while same number of molecules now will be when shifting to the corresponding solid phase. In case of solid phase, they will be occupying the fixed crystalline structure, and in their crystalline structure there will be formation of hydrogen bonds, which will be creating the extra void spaces and will avoid hindrance to fit the molecules closely with each other. Okay. This point is clear?
Yes, sir.
So this particular part actually I'll discuss in our next lecture also.
Yes, sir.
Okay, now the question is, we apply heat from outside the container, but still the temperature is constant. How? Okay, so what we are doing actually, first thing is we are moving through the quasi-static process. So the rate at which we are adding the heat, first it will be heating the container, and then after that there will be transfer of heat from the container to the medium. So that's why our medium will be almost at constant temperature, because we will try to maintain some steady situation where we will keep on adding the heat unless or until our fluid temperature is actually maintained at a constant value. Is this point clear, Kusagar?
Yes, sir. Sir, I have a doubt. Do we use some specified walls of container for this?
Yes, sometimes we use specified walls also. Are you you are registered in which program of engineering?
Engineering physics.
Engineering physics. So probably you may also end up in taking subjects like heat transfer. So there you will be having like more detailed elaboration that while we design the thermal system, what considerations we have to consider. Okay.
So other factor may not be taken into consideration, like pressure is decreasing and volume is increasing, but still temperature can be constant.
Yes, temperature can be constant. Yes. So we may have some situation, we may devise a system which will be maintaining the temperature at constant value. Okay. So normally what we do, we are having some feedback based controller, which will be actually continuously monitoring the temperature of our system. And if temperature falls below certain critical value, heater will be switched on. And if it goes beyond some critical value, heater will be actually switched off. So within some limit of temperature close to our set temperature, we can actually maintain the medium. Okay.
Okay, sir. Thank you.
Then the next question is, in TV graph, liquid vapor region is present. Where is the corresponding region in PVT graph? Okay. In PT graph, so the Aryan response is, in case of PT graph, whatever the liquid vapor region we are having, that appears as a single line. Okay. So we are not having detailed region that is not visible, because PT graph is nothing but plotted along in a direction of the volume. So while we will be taking the projection, actually both the saturated liquid line and saturated vapor line will be coinciding on a single line. So that's why that line actually itself includes both the regions, and we cannot see the details. Is this point clear?
Yes, sir.
Next question is, please explain properties of dense fluid above critical point like boiling point. So that's very difficult to tell, as I have already specified you that above critical point we are not having any definite boundary which represents the transition from this one, which represents the transition from liquid phase to vapor phase. However, the only thing is that we will be having temperature always greater than 374 degrees Celsius and pressure always greater than 22.09 megapascals. Okay. However, exactly we are not able to specify the property. It's a part of research. Many people are trying to obtain the boundaries beyond critical point for the demarcation between liquid and vapor phase. Okay. Rehan, clear?
Okay, sir.
Okay, so is there any other question?
No.
Anyone else is having any other question? Okay, so in that case, it's good. Today, all the questions are over. And we are having very short doubt clearing session in comparison to other sessions.
Excuse me, sir.
Yeah, please.
Sir, my doubt is not clear, sir. It's number 112. So I was having that issue. So I couldn't.
112, which question? Okay, Asutosh, above critical point, dense fluid, is there any boundary line in the graph? Okay. So that's what just now I answered, Asutosh, that we are not having any exact boundary which is known yet, which shows the demarcation from liquid to vapor phase, and still people are doing research in this area, and they are trying to obtain some transition boundaries for demarcation between the liquid and vapor phase above the critical points. Okay.
Sir, I'm asking, that we have mentioned the is there any line that above this the dense fluid starting below this there is gas exists and liquid exists separately?
That's simple. You seen on PVT surface the pressure line corresponding to 22.09 megapascal is that boundary line. Okay.
Yes.
The pressure line, constant pressure line corresponding to 22.09 megapascals is that boundary line which represents the demarcation of individual liquid and vapor phase from the dense fluid. Okay.
Okay, sir.
Okay, so is there any other question? Okay, if not, so I am now stopping this recording.